Hey, 11th graders, and welcome to Unit 2. So, we are continuing with geometry. We're still doing a bunch of geometry. We're now moving on to the more complicated of geometry stuff. So, we ended last unit with talking about only right triangle trigonometry. Only right triangle. So, things that are only right triangle trigonometry are Pythagorean theorem, can only be used for right triangles. SOHCAHTOA can only be used for right triangles. Now, in this unit, we're going to start to learn and talk about non-right triangle trigonometry. And non-right triangle trigonometry can actually also be used for right triangles. But sometimes that gets bled over a little bit for students that they're like, okay, well, I can use non-right triangle stuff on right triangles, but I can't use right triangle stuff on non-right triangle stuff. And so I just highly encourage you to keep the things separate. Pythagorean theorem, SOHCAHTOA can only be used on right triangles, and sine rule, cosine rule, area formulas just really should only be used on non-right triangles. So again, the things that we're going to learn in the lesson today and for this first lesson are going to be things that you can use on right triangles, but to just keep things in nice, neat categories, we're going to say these can only be used for non-right triangles. All right, law of sines. When we're talking about non-right triangles, we have a couple different ways that we can solve for angles of or side lengths and angle measurements. The sine rule or the law of sines is one of those ways that we can solve for either a side length or an angle because we can't use SOHCAHTOA anymore. So we have to have other things that we can use. So what I would like for you to do is first just draw a triangle of any look or feel as long as it is a non-right triangle. And then I would like for you to label your vertices with uppercase letters A, B, and C. The thing with all of these rules that we're going to learn with non-right triangles is that we have to be able to establish relationships of side lengths to each other. And how we do that is with uppercase and lowercase letters. Uppercase letters will always be your angle measures, and the lowercase letters will always be the side length opposite of the uppercase letters. So lowercase will always be a side length, uppercase will always be an angle, and the relationship is that the uppercase angle is opposite of the lowercase side length. For instance, A, the side length opposite of A, we can think of it as a spotlight, is going to be here. So that side length is lowercase a. C's opposite side length, is going to be here. And then B's opposite side length, shabam, here. So all lowercase opposite side lengths of the uppercase angles. The law of sines is in your formula packet. I would like for you to go and find, it's called the sine rule in your formula packet. I would like for you to go and find in your formula packet the sine rule. If you don't have your formula packet in paper in front of you, it is available on Schoology in your classroom information folder. So right now, I would like for you to tell me what page is the sine rule on in your formula packet. The sine rule formula is on page 6 of your formula packet. Notice that at the top it says topic 3, geometry and trigonometry. And there it says sine rule, cosine rule, and area of a triangle. Now I'm going to give it to you in a different way than your formula packet gives it to you. I've always learned that it's sine of uppercase A over lowercase a equals sine of uppercase B over lowercase b, sine of C over C. That is your sine rule. It is totally fine if you did the flip of it, as you can see in your formula packet, that lowercase a divided by sine of a is the same thing. Now, it's given to us in threes, and so a lot of times students will be like, I have to set up those three relationships, but all it means is that the sine of any angle divided by its opposite side is equal to the sine of any other angle in this triangle divided by its opposite side. So I could do sine of A over A equals sine of B over B, or I could do sine of A over A equals sine of C over C. Or I could do sine of B over B equals sine of C over C. All of those are true. And we only want to set up two equations being equal to each other, because how weird does that look to have two equal signs with three different things? We don't like it. We don't work with it. It's not something we're used to. And it's not something we really do in mathematics. So it's really only two of those ratios. All this means is that it's the sine of any of those angles divided by its opposite side. It's saying it's true for all of them. All right, so our first example. We want to find the value of the missing side length of x in the triangle. We want it to two decimal places. Hey, that's important. I should underline that to remember. Okay, so all we're talking about with all of our rules, sine rule and cosine rule later, is an angle and its opposite side. So notice we've got an angle and its opposite side here. I could label it A and A if that helps. And then I've got an angle and its opposite side here. And maybe I'll call that B and B. So then that's the relationship of the sine of an angle divided by its opposite side equals the sine of any other angle divided by its opposite side. And I could have flipped it and had sine of 65 over 14 equals sine of 25 over x, or I could have x over sine of 25 equals 14 over sine of 65, right? So we can, as long as we keep it proportional and change it in the same way, then these relationships are fine to move around. In order to solve for this, we can cross multiply and then divide, right? So cross multiplying 14 sine of 25 equals x times sine of 65, and then divide both sides by sine of 65. And if you put all of that into your calculator, it will give you a value. Or you could plug this original equation into your numerical solve. TI Inspire's numerical solve is menu, algebra, numerical solve, and then do sine of 25 divided by x equals sine of 65 divided by 14, comma, x. Ta-da! 6.53. Or you could have just plugged in this whole piece and just, not the x equals, just this, because this is just a number. It is very specifically 6.53, give or take. Two decimal places, centimeters. Don't forget to use your numerical solve. TI 84s, it's in, I think, math, and then you scroll up and it's solver. I think. Ask me when you come to class, and if it's not there, then we can go through that together. All right, and that's it. That's how you solve for a side length of a non-right triangle. So gone are the times when it's a non-right triangle, gone are the times that we use SOHCAHTOA. So then we have to shift our focus and say, okay, I can't use SOHCAHTOA because it's not a right triangle, so I can use the law of sines or the law of cosines, which we'll learn here in a second. Okay, we can also then use the law of sines to solve for a missing angle, just like we could use SOHCAHTOA to solve for a missing angle, but since it's not a right triangle, we can't use SOHCAHTOA, so we have to use law of sines. Notice angle, opposite side, angle, opposite side, and in that relationship, I only have one unknown. With a lot of this, if you set up a problem using law of sines or law of cosines, and you notice you have more than one unknown, more than one variable, then you've set it up using the wrong equation, and then you just use the other equation. So we go through and set up that relationship. Sine of theta divided by 10 equals sine of 60 divided by 9. We could, I believe, yes, we could use numerical solve to solve for this, and it will give you an answer. It will give you only one answer of possible two answers. So this is where numerical solve can be a little bit tricky. Let's talk about how to use not numerical solve, and then I'll talk to you about why there's actually two correct answers for this. In order to solve for an angle, when a variable is trapped inside of sine, any trigonometric function, we have to use inverse sine or inverse trig in order to get it out, right? The only way to get our variable out to say theta equals without a sign next to it is that we have to use inverse and flip our inputs and our outputs. But it's a little bit unclear here right now what is an input and what is an output because sine of theta is not by itself. So when you're solving for an angle, you need to use inverse trig. Before you can use inverse trig, you need to get that trig function by itself. So isolate sine of theta, which in this case is pretty straightforward. I just multiply both sides by 10. Sine of theta equals 10 times sine of 60 divided by 9. And that is approximately 0.962. You can type it into your calculator and it will give you a value. So when we have an input of theta, we have an output of 0.962. And once we get to that, sine of theta equals a number, we have isolated for sine of theta. And then we can do inverse. So now I can say, oh, well then just the inverse will flip these two. Really, really important with trig. Do not type in 0.962 into your calculator. You need to use the exact value that's in your calculator. So for instance, 10 times sine of 60 divided by 9 equals that, right? If I do inverse sine of that exact value, which how I use that exact value is I scroll up until it's highlighted and then I press enter and it brings that value down inside of my inverse sine. I can press enter and I get 74.2, which is 100% correct because I've used the exact value in my calculator by scrolling up and pressing enter. If I did inverse sine of 0.962, it might slightly change it. See how it's different? So if I wanted it to 3 decimal places, this would be wrong to use this. And so you can see that with trig especially, we need to make sure that we always use the exact value, not the rounded value. The reason why we put rounded values on paper is as a placeholder. It's about this, but I know that it's not the complete idea, or it's not the complete of that number, but it's more of the idea of, okay, this number that I've got in my calculator to remind me myself to go grab that number in the calculator. Yeah, so our final answers should always be using the answers that we use in order to get our final answer should always be the exact value of what we had before, not ever the rounded version that we put on our paper to kind of keep track of stuff.